Good morning, everyone. My name is Kyrian Adimora. It is my great pleasure to present our research on GNN and Intelligent HPC Resource Scheduler. This is an ongoing research. The first phase of this work was presented as a poster in the just concluded Supercomputer International Conference in Atlanta. First, before we move on, I would want us to actually understand what is high-performance computing cluster, what is resource scheduling, and what is job scheduler. Most times, when we talk about high-performance computer, people will be thinking as something that is abstract. Have you actually imagined why do you use AU cluster to do your research instead of working on your computer? So these blocks here represent the HPC high-performance clusters. The job queue here, remember, is like applications you submit to run on the cluster. The resource scheduling is like a manager that takes care of these jobs as you submit them and place them appropriately on the cluster. Now, what this implies that imagine you have a puzzle to solve. This puzzle takes many years for your laptop or your computer at home to solve. Then HPC is like team of thousands of powerful computers solving the same problem much more faster. They are spatial computers, much more powerful than our conventional computers. So they are connected in a way that they work together to solve problems. Now let's look at resource scheduler like a manager in a very busy restaurant kitchen, like a KU dining, where you have many chefs, you have many orders, and you have to decide which chef to make which dish. And you equally want to decide when should they start cooking, how to make sure that no chef is sitting while others are overwhelmed. You want to actually get all these orders out as faster as quickly as far as it is. So this is the same thing that the resource scheduler does. You submit your applications, the resource scheduler looks at the runtime estimation, the core requirement, and place it appropriately there. So the resource scheduler is a very critical component in the HPC context, because what it does is that the HPC system is very expensive to build and to run. Researchers, engineers make use of HPC to do their work. So our interest here is that we want to make sure that HPC facility, every aspect of it is maximized completely. So by proposing an intelligent hybrid graduate reinforcement learning and a graduate neural network with the reinforcement learning capability to solve this problem. The GNN part of our work is like giving a map to reinforcement learning, to resource scheduler, to understand how all the computers are connected and the different tasks, how they are related. Then why the reinforcement learning component of our model is like training the resource scheduler on how to solve this problem so that over time, as it's allocating resources, it becomes more efficient. Currently, the HPC workloads are becoming very complex. So because of that, it places a limitation for traditional scheduling approaches. So this sketch actually can exhibit the current problem facing the HPC's workload problem. One is that when we look at on the blue color, we see the traditional workload. It has a gradual linear growth complexity over time. On the red line, we have the evolving AI workloads, exhibiting a steeper and exponential growth in complexity over time. Then the resource for compute, the demand for compute, is showing a very critical complexity over time. So this places limitation to the approach that is used for scheduling this time. So this is where many researchers in machine learning have actually contributed presently to see how to solve this problem. But unfortunately, they have not comprehensively modeled the complex interaction between jobs, the resource requirements, and the state. So especially when it comes to temporal and the spatial complexity inherent in the HPC workload. This is where our research comes in. This is actually created a research gap we are solving. So our research addresses this limitation through these research contributions. What we do, we implement a hybrid approach of a GNN and reinforcement learning to actually model this complexity more effectively in the HPC workload environment. We developed an adaptive reinforcement learning system that will be able to optimize the scheduling decisions and through the replay and action process. So we equally develop the algorithm that actually optimizes the resource utilizations, throughput, the fairness of the system simultaneously. And we conducted a very extensive experimentation to actually validate how our model is working using the real-world workload traces from the Argonne Leadership Computing Facility in Chicago. And our model was able to perform extensively well over the existing algorithm. So this slide actually presents our GNN. You can see the GNN here means graphic neural network. YDS is the reinforcement learning. The base model architecture overview. This is the architecture overview of our model. Then it primarily consists of three important components. One is the GNN component, the replay buffer, and the reinforcement learning component. What does this architecture entails us? When we look on the left here, we see the job queue, the job submitted, the application you run on your cluster. These are the job queue, the computational jobs. So these jobs enter our system, and the GNN component, this year we are using graphic attention mechanism. So our GNN processes this job using graph attention network layers. We have these three layers. We define three layers: layer 1, layer 2, layer 3. So layer 1 actually processes the resource feature. So this resource feature means the hardware specification requirements, the CPU, the memory, the GPU, the storage, the network. And it is essential for you to know the resource requirements of each job that is submitted. That is the sense of that layer. Then the second layer, the layer 2, models the time feature. That is, here we consider the expected runtime of each job. Then how long this job spent on the queue, and any deadline that is possible. So it helps us to actually model time-sensitive job workloads in the HPC system. The third layer here actually looks to job priorities like job types, the priority level, then any dependencies attached to that job. So it helps us to actually, at this point, to formulate the execution order of the jobs. So the output of all three of these layers are now fed into a multi-head attention mechanism. So this is like multiple experts working together to actually handle different scheduling problems simultaneously. So this component is what actually helps our model to understand the complex relationship between job complexity and their resource requirements. And on the replay buffer here, what replay buffer does is that it stores the past scheduling decisions and the outcomes. So which is very important for learning experience. On the right here, we have the main man, the reinforcement learning component. So with a priority scheduler, this is where the real decision making takes place by determining the core allocation of resources based on all the processed information here. So what actually makes this architecture so powerful is the ability to combine the capability of pattern recognition, capability of GNN, and the decision-making capability of the reinforcement learning, integrating this capability, creating a scheduling algorithm that can learn and adapt to changing HPC workload. So we actually try to developed the GNN part of the algorithm using attention-based message passing. The core essence of bringing this implementation, this message passing into our implementation, is to allow the jobs to communicate their state and their resource requirements to each other across the graph structure. So this communication we found is very essential for us to actually, for the model to make a better intelligent scheduling decisions. So then by understanding the individual job characteristics and how they relate to each other. So when we look on the left side here, we can see the input jobs, J1, J2, J3. These jobs are interconnected. So they are interconnected, indicating their relationships in terms of the source, the resources they share. So, and we see the dashed arrow. The dashed arrow here is the attention weight. This attention weight dynamically computed for a pair of jobs. Like we can see attention weight for job 1 and job 2, and attention weight for job 1, job 2, and job 3 is computed using this mathematical equation. This is, we could call it attention coefficient. So what it does is that it is the coefficient that we use to measure the importance of relationship between a job and a job. So that is what that does. And then when we look at the middle here, we see the green boxes labeled the graph attention layer 1, layer 2, layer 3. But there is one important thing here. That is actually the great aspect of our component design. We have the forehead here, we have 2 heads here, we have 3. So there is a progress reduction in the head. So the first head that has the largest heads, what it does is that at the first instance is interacting with the system jobs. It captures all the necessary features, the aspect of the system. Then at that time, both the necessary and unnecessary. Then the reduced head here will be able to filter, consolidate that information and refine them. Now push it to the one that has the head 1. The head 1 now will be able to concentrate on because it produces the final graph embedding system. So that will produce the core results. That core result is what we see as updated job representations in the form of this. So it contains the individual job characteristics and the informations relevant for our model to take intelligent decisions. So this is the reinforcement learning component of our model. So you see facilities that the RL agent is using to make that decision. So the graph embedding is the output of the GNN, the graph attention network. So now the RL agent is the decision-making agent. It interacts with this, converting this graph cluster, like the cluster of the cluster state, converting it to scheduling policy using the policy network. The policy network, what the policy network does is that the policy network actually generates the decision scheduling for every job that comes in based on the current state. And the experience replay stores the past scheduling decisions, for every job for learning purposes. The reward function here balances the competing objectives. Maybe want to balance the model wants to balance the resource utilization against the job throughput and the system fairness. So that is what the reward function does. The state space here captures the current state of the system, which could be maybe the computing resources, the compute node resource utilization, the queue status of the pending jobs, the execution progress of the running jobs. So the action space is the intervention that is available for the reinforcement learning agent to actually take place. These features are what the RL is using to actually transform the graph embedded. So this actually the technical detail, the GNN-RL technical implementation details. So we have the algorithm, we have the flowchart. So if you didn't understand the algorithm, you could grab the flowchart easily. That is why we made it available on this slide. So here, what this means is that we have 2 important sections, 2 functions. One here is the training model. We have the scheduling decision model. So this one takes the scheduling decision, this one training the training of the model. So we implement this, our model in the first place by leveraging the graph attention layer 1, layer 2, layer 3 with a decreasing head order of 4 to 1. Then the reinforcement learning actually takes decision based on the policy network by generating the scheduling decisions. And actually at this point, what it does is that for each job based on the current state, then the replay buffer, we define the replay buffer with a limit maximum length of 10,000 entries so that when it gets full, our network can get updated. For each epoch in our training, because we use a PyTorch for this training, so for each epoch, we create a graph. The V here means the node, the job, while this is the age, this is the graph. So for each job feature is incorporated with 3 key dimensions: the node characteristics, the core requirements, the runtime estimates. So we now curate the age index. The age index based on the temporal relationship between jobs. So this now will help us. We'll look at the H1 here. The H1 is the output of the first layer. So that is the first output that have a lot of information. The H2 is the output of the second layer. The third H3 is the final output that we need. So this final output now is now transformed to state representation through a fully connected layer named state FT. So then now map it into the action probability via the policy network that takes the decisions for the scheduling of our work. Now, the reward function is computed based on these key metrics: the resource utilization, the throughput, the fairness, and our max spend. So we keep on storing this state action reward. We keep on storing them on the replay buffer. Once the replay buffer is full, our model network is updated. So that is how the process keep on iterating. Now, moving to the scheduling function section, what the scheduling are, remember that from the first slide, I showed you the scheduler and the job queue. So every job in the queue, we sort this queue based on the arrival time and the priority. So, now we compare each job, the specification, the cost specification with the available resources for computation. If it is less, then we schedule the job. If it is equal to, we schedule the job. But if maybe it is greater, the job will be kept in the queue, and that could lead to starvation. That is it. So we keep on working until going through all the jobs in the window until no job is there. So we process the next batch of job, extract features, now compute the H index using the temporal relationships, then compute the job priority. The job priority could be maybe the deadline jobs. Like now, before you came over here, you may have some other scheduling, but the one that is most pressing is this, and that is why consider those priority. So the job priority, based on that, we now sort jobs based on the priority, still check their resource requirement. If the resource requirement is less than the core available, then we schedule the job. If it's equal to, we schedule the job. But once it's greater than, so we leave the job on the queue, and the job will be there. So this process continues. This is the implementation details of what we actually did to achieve this ongoing work. So this is the implementation of a feature processing pipeline. So what do we mean by feature processing pipeline? Now, initially, I was like talking about the job features. Each job. So our scheduler implement a sophisticated feature processing pipeline to extract the resource requirement. If you look at resource requirement here, you see time metric requirement, the job feature requirement, the job property requirement, the historical data requirement, the user group requirement. So all these features will be extracted and now pass through our GNN model. So using these features and the H index, remember that the H index is the temporal relationship between the jobs. And now this will now be computed using compute the job priority. Now we compare these jobs, the availability of the compute resource with the core requirement. Once the job that we are trying to schedule is enough to pass through the available compute resource, then we schedule the job and update. But if it is not, we'll push it back to the queue and you stay there. So this process iterates. So this is the flowchart. This is the algorithm for better understanding of our implementation. So this actually shows our GNN-RN framework technical details. Why do we say the technical details? We really want us to understand the training and inferencing process regarding our work. So here, our training process utilizes GPU through a batch processing technique. The input jobs are they are being processed in batches where the GNN construct a graph structure based on the job features and the resource states. So both the GNN and the reinforcement learning jointly optimize by computing the load, they're computing losses and they're performing back propagation. So through the entire system. Our model parameters are updated by using the gradient-based optimization to improve the system performance. Now, these trend models, the GPU accelerated we used significantly perform better in terms of training time overhead compared with a CPU-only implementation for HPC scheduling environment. So this trend, the GNN and the reinforcement learning models, we use them for our inferencing here. So we use them to actually make scheduling decisions, optimize our resources, and monitor the performance of our work. So the policy network in the reinforcement learning, what it does is that it generates scheduling decisions and actually for every incoming jobs based on the current state. And the action selections reward computation here optimizes the resource allocations for each for our system. Our system continuously being evaluated for its performance monitored. If there is any issue, it now gives feedback to the training process, and that feedback will be the thing will be improved again. So that is the process that actually takes place in this. The good thing about our model is that the flexibility. So this slide actually shows how our model is integrated with SLUM. SLUM is a scheduler that we use in the HPC. We have SLUM, we have a PBS, and a lot of them. But SLUM is our interest. We are trying to improve the SLUM as a resource scheduler. So the seamless integration of our model. So this actually, this architecture shows the integration of our model into a SLUM. And it has primarily 5 different layers, and each layer contributes to the capability of decision-making of the system. So the layer 1 we can see here is the user interface. That is the entry point where you and I, we submit our application to the batch system, to the cluster, but it maintains compatibility with the SLUM command line interface, while abstracting the underlying AI-driven complexity from the end user. So this ensures the friction-free transition from the conventional scheduling to our implementation scheduling. The control layer here houses the SLUM controller and our GNN-RN model. So the GNN model here model the state cluster into graphs, and this graphs now is being utilized by the reinforcement learning for scheduling decisions. And the queue management layer here, this queue management layer implements an queue-based intelligence system that respects the traditional approach of first come, first serve, and the graph-based representation. So this dual representation actually made our model to perform extensively well in the form of a resource utilization and that throughput. So the execution layer manages the actual computation. You can see the compute node and the storage here. So, and give feedback to the AI components. So this bi-directional communication is actually what makes our model to perform exceedingly well in the MEXPEC. As we can see in our result, maybe in a subsequent list, the AI optimization is the core innovation. That is the innovation of our work, where the graph output, the graph embedding is now being transformed into scheduling decisions. So the performance metrics here, they keep on monitoring our model based on the four key metrics: the MEXPEC, the throughput, the resource utilization, and the fairness. So in actually, for us to validate the effectiveness of our model, we conducted an extensive experiment using a workload traces from the real-world HPC environment in Argonne Leadership Computing Facility. So the data set we actually used is a record of scheduling jobs data set for 3 key major supercomputing machines: the Polaris, the Myra, the Colli. So these are what we used. We can look at this, we can see that the Polaris has the highest data set, and followed by the Colli next this. So in our algorithm design, you know that we look at the worst case scenario for us to actually know how long the algorithm works with the time complexity takes. So our algorithm performs well with the data set that has the highest data. What happens to the algorithm when the data grows, not when the data is small? So we can see from our result. So our experimental setup involved these hardware implementations, where we use Intel 7 CPU with 64 cores and the 256 gigabyte RAM, the embedded GPU 800 with a 40 gigabyte memory, the operating system for 5.15 Linux. The reinforcement learning scheduling metrics actually here, when we look at this, we can see this color is the same. So the uniform distribution of the heat map is the state representation of our model. So what this suggests is a balanced state exploration, indicating stability in training and in learning of our model. Then here is the reward history to actually investigate the scheduling position of the data set we used. The linear reward growth shows that our model is learning efficiently. And this moving average reward actually confirms this, showing the behavior of our model in terms of the training. So this table presents the performance algorithm for performance algorithm results on different machines. For the Polaris and the Coley machines, our model achieved the best result here. The resource utilization, I really just want to flash it back, means the percentage consumption of the system by the algorithm. While the throughput here means the total work done by the algorithm. The fairness here means how fairly the resource allocation is allocated to across all the algorithm. The max spend the total time it takes for the algorithm to complete all the jobs. So for the Polaris and the Coley, our system actually achieved the best. And for Myra, it achieved the 84.25% in resource utilization, but a competitive result in throughput and the max spend. So our Polaris data set result shows here, we can see that our model achieved the best in resource utilization, the best in throughput, the best in max spend. For Coley, our model achieved the best in resource utilization, the best in throughput, and the best in max spend. The Myra, our model achieved the best in resource utilization, the competitive result in throughput, and the competitive result in the max spend. So this actually, our investigation on this actually shows that the result we have, that our model have been able to demonstrate the remarkable improvement in resource utilization, throughput, max spend, and system fairness compared with the existing approach that used in scheduling. So our future work, we are planning to explore a hybrid approach of attention mechanism for better workload pattern recognitions. We're equally trying to see a way of implementing a multi-objective optimization framework that will incorporate energy efficiency. Thank you. And I can now have questions. Thank you.
You're a little bit over time, maybe one question.
Have you looked into using the I2S cluster resources to test out your model?
Could you please come again? I didn't get you.
Have you looked into using the I2S cluster resources to test out your model?
Oh, I have not tested that. I have access with Argonne Leadership Computing Facility even up to 2026 August. So I have access to the Celebrates, to GraphCore, to a lot of this, to their cluster. So I'm using it for my experiments, not the school cluster.